Hello, this is Group 22 for EME 303, and we studied what causes the trajectory of a tennis ball after making contact with a tennis court. The contributors are listed on this slide, and how we went about this is by first observing what occurs pre and post contact with the surface, and then hypothesizing what occurs depending on different variables. Then we went about actually understanding the physics behind the variable changes and what results are expected and do occur from these variations.
Here are some observations of the tennis ball before it hits the ground. However, before we talk about that, let's talk about the Magnus effect. The Magnus effect causes an additional force on a spinning object, or in our case, a tennis ball. A tennis ball spinning causes unequal drag forces on top and bottom. Reference the illustration at the top, and notice how different drag and pressures around the ball would change its direction through the air. The first spin we will look at is a flat spin. This would be no rotation with any angular velocity through the air. Due to this, the ball does not experience Magnus force. However, it does experience ordinary drag in the opposite direction of velocity. If you wanted to solve this equation here would aid in doing so. For the next spin, of top spin, we do see Magnus force being caused. The difference in air pressure and drag direction acts as a downward force, which would push the ball down quicker. Finally, backspin would also experience Magnus force. However, the difference in air pressure and drag direction would cause a lifting force. The two illustrations in the top right and bottom right show both the differences in trajectory of the ball relative to the type of spin. And also, in the bottom picture, it shows how the different spins are influenced by drag, lift, and gravity.
After the tennis ball hits the ground, we can make several observations. Comparing the top and back spins, we can see that vertically both spins cause the ball to bounce at the same height and speed. Horizontally, a ball with a top spin will travel faster than that of one with a back spin. Additionally, the post-bounce angle of the top spin is shallower in comparison to the back spin. Comparing a grass versus clay court, the speed in which a ball leaves the clay court is faster than that it would leave the grass court, and a tennis ball will bounce almost twice as high off a clay court than it does a grass. For a tennis ball with no spin, the post-impact trajectory angle is between the top and backspin angles.
We hypothesize that when the ball comes in contact with the court, some kinetic energy is lost and dispersed into heat. During topspin, due to the direction of the spin, the friction force is decreased, and it'll accelerate towards the y direction than would in x, so it has more of an arc to it. During backspin, it spins in the opposite direction, and the friction force is increased and may cause the ball to skid until it changes completely into spin. Kinetic energy is lost during the transition, and when it becomes airborne once more, we believe it will accelerate further in the x direction than would in the y. So this force path of travel will be more parallel towards the court. During flat, due to having no initial spin, we assume that when it comes in contact with the court and becomes airborne once more, the acceleration will decrease significantly both in x and y direction, so it'll leave at approximately the same angle and go about the same sort of distance.
From the time the tennis ball leaves the racket, friction forces are apparent throughout the ball's entire journey. From the impact with the racket, the friction of the strings imparted on the ball creates a spin on the ball. As it's flying through the air, the ball experiences a drag forces like air resistance, which can be calculated by the equation drag equals rho v squared AC divided by 2. When the ball makes contact with the ground, there are 3 scenarios which affect the friction forces: topspin, backspin, and no spin. Topspin is when there is a forward spin on the ball which reduces the net friction that it makes at contact. The friction forces will point in the direction of the horizontal velocity, and the angle of incidence will be greater than the angle of reflection. For backspin, the ball skids on contact and experiences kinetic friction. The increase in net friction reduces the horizontal velocity, increasing the angle of departure, and this kinetic friction can be calculated using the formula frictional force equals mu k times the normal force. For no spin, the friction force on the ball acts in the direction opposite of the horizontal velocity. The friction imparts a small amount of topspin on the ball after it makes contact with the ground, and the angle of incidence is almost equal to the angle of reflection for the ball when it makes contact with the ground.
In application, the trajectory of the ball after making contact with the court's surface will be dependent on the spin type and the surface type of a court. In tennis, there are several types of courts, but for analysis' sake, we'll focus on the four listed above, respectively being red clay, hard surface, grass courts, and green clay. Now, combining these surface types with any kind of spin could produce any sort of resulting trajectory, and so we'll first focus on the courts alone. Looking at these surfaces, they are rated on a scale of quickness, meaning that they are either rated faster or slower. A fast court causes bounce from a ball that would be faster after contact with the surface but bounce lower to the ground, while a slower court causes the bounce to be higher but move slower. In fact, there's even a method of calculating what is called court pace via the equations shown, where mu is friction force, E is the coefficient of restitution, and A is the pace perception constant. The results of this show ratings above 45 as being considered fast and below 30 as slow. Now, looking at the examples provided, we see more rigid surfaces like hard quartz will be fast, while clay quartz and other materials will be slower. This is due to the fact that on less rigid surfaces like clay, the contact from the ball causes a depression into the clay, as to which the ball has to climb out of, making the movement slower and the bounce higher, as it acts as an inclined surface. Then, considering spins, the notion follows that the more topspin used will mean the less effect friction will have on the trajectory, and therefore causing a higher bounce. This notion works in the sense as well that with topspin being decreased to the point of being backspin, then friction is very much present and plays heavily into the trajectory, causing a lower bounce and little distance to be covered. The models to visualize this phenomenon are shown between ground strokes with no spin and with topspin on the bottom right.
In conclusion, for the physics of a tennis ball, during mid-flight, some of the forces acting on it include drag forces due to pressure difference, and the Magnus effects creates a spin on the ball. It either creates no spin, backspin, or topspin. Also, acting on the ball during its journey is friction. Friction acts on the ball from the moment it leaves the racket. Friction is responsible for giving the ball its spin. Some types of friction that are acting on it are drag forces like air resistance, kinetic friction with the ground, and these acts either with or against the direction of horizontal velocity when it makes contact with the ground. And from this, the bounce. Friction, velocity, and type of spin are all limiting factors that affect the degree and direction of the bounce after the ball makes contact with the ground. Backspin will give it a lower bounce, front spin will give it a very high bounce, and no spin equals the angle of incidence will equal the angle of reflection.